Hello students, welcome to Jnanataranga CET NEET coaching classes. This program is organized by Pre-University Education, Government of Karnataka and myself Ravindra Swami, and today we are discussing an important chapter, moving charges and magnetism. Okay, you know that if a single charge is placed in an external electric field, it experiences a force, that is F equals Q into E. Okay, so in case of electrostatics, the force on a charged particle is always in the direction of electric field. But now we'll see what happens in case of magnetism. Okay, so whenever if charged particle enters the magnetic field, it experiences a force. That force is given by vector F equals Q into V cross B. Okay, so this expression shows that when a charged particle enters the magnetic field, when it experiences force, that force is always perpendicular to the direction of velocity and also perpendicular to the direction of magnetic field. Okay, so force is perpendicular to velocity and also perpendicular to direction of magnetic field. Angle between velocity and magnetic field can be anything, but remember, angle between force and velocity is always 90 degrees and angle between force and magnetic field is also 90 degrees. Okay, but in case of electrostatics, we know that the direction of the force and direction of electric field both are same direction. Okay, that's why these lines are called as electric lines of force. But in case of magnetism, suppose if you take these are the direction of magnetic field lines, we know that now direction of the force and direction of the magnetic field are perpendicular to each other. Okay, so these lines can be called as magnetic field lines only, but these lines can be called as electric lines of force. This is a basic difference between electric field and magnetic field. Okay, and one more thing is, you know that when force is perpendicular to velocity, this force can change only direction of velocity of the charged particle, because in case of electrostatics, what happens whenever if charged particle enters the magnetic field, when it experiences force, the force changes the magnitude of velocity of the charged particle, and in some cases it may be direction also. But in case of magnetism, whenever if charged particle enters the magnetic field, now when it experiences force, remember this force can change only direction. If it is uniform magnetic field, only direction of the velocity of the charged particle changes. Okay, magnitude of the force always, magnitude of velocity of the charged particle always remains as constant. Okay, and the same concept we have studied in first PU also, that is whenever if force and velocity are perpendicular, the in case of when particle is moving along a circular path, we know that force can change only direction of velocity of the charged particle, but magnitude of the velocity of the charged particle always remains as constant. Okay, so we'll discuss few special cases based on this expression. You know that we can write this in magnitude of the force as F equals QVB sin theta. Okay, first case, if you take theta equals 0, theta equals 0 is nothing but velocity of the charged particle and magnetic field both are F equals QVB sin theta. Okay, when you write magnitude of this force, F equals QVB sin theta, if theta equals 0, that is velocity of the charged particle and magnetic field are both same direction. In that case now, the force on a charged particle is 0. And in this case I can say particle moves along a straight line path. Okay, even if you take theta equals 180 degrees, that is velocity and magnetic field are in opposite direction, in that case also force on a charged particle is 0. So these two cases shows that whenever if charged particle enters in the direction of magnetic field or in the opposite direction to the magnetic field, it does not experience force, and in these two cases now particle moves along a straight line path. Okay, suppose if you take one more case, that is Q equals 0. Q equals 0 is nothing but particle does not carry charge. For example, if you take neutron, when neutron enters magnetic field, it experiences no force. Okay, similarly when neutron enters electric field also, it experiences no force. Okay, so one more case I can take third case as velocity of the charged particle is 0. When velocity of the charged particle is 0, that is nothing but the charged particle is at rest in a magnetic field. When charged particle is at rest in a magnetic field, remember it does not experience force. It does not experience force basically because when the particle is at rest, it does not carry current. If there is no current, there is no magnetic field. Basically, the particle experiences force because the interaction between magnetic field produced by charge and as well as external magnetic field. Okay, but in case of electrostatics, what happens when the charged particle is at rest? It experiences force, because you know that stationary charges can produce the electric field, but only moving charges produces the magnetic field. Okay, so if any particle has to experience force, there must be interaction between two fields, minimum two fields. Okay, so in case of electrostatics, what happens? Stationary charge produces electric field, so there is an interaction between field produced by stationary charge and as well as external electric field. Therefore, it experiences force. In case of magnetism, we know that stationary charge never produces the magnetic field, so there is no interaction between the two magnetic fields. Therefore, I can say force on a charged particle is 0. Okay, and one more we will take important case, that is theta equals 90 degrees. Okay, theta equals 90 degrees. In this case, the charged particle experiences maximum force, that I can write F maximum equals Q into V into B. Okay, and if you want to find the direction of the force in this case you can find by using Fleming's left hand rule. If it is not equal to 90 degrees, then use this cross product rule, but when it is equal to 90 degrees you can use Fleming's left hand rule. According to this rule states that if the first three fingers of the left hand are stretched such that they are mutually perpendicular, so that the forefinger gives the direction of magnetic field, middle finger gives the direction of velocity of the charged particle, then the thumb represents the direction of force. Okay, so easily we can find the direction of the magnetic force using Fleming's left hand rule. I repeat this once again. If the first three fingers of the left hand are stretched such that they are mutually perpendicular, so that forefinger gives the direction of magnetic field, middle finger gives the direction of velocity of the charged particle, then the thumb gives the direction of magnetic force. Okay, so but in this case we will discuss the particle moves along which path, because you know that when theta is 0, particle moves along a straight line path. When theta is 180, then also particle moves along a straight line path. But when theta equals 90 degrees, we will discuss particle moves along which path. Okay, suppose if you take direction of the magnetic field as inwards, inward magnetic field is denoted by cross. Okay, so if a charged particle enters this magnetic field with a velocity v, now you can see velocity of the charged particle and magnetic field are perpendicular. So in this case, if this is the direction of velocity of the charged particle, magnetic field is into the plane of the board, force is acting in upward direction. Okay, so because of this force, instead of moving along straight line path, particle starts moving along this path. Initially it has velocity this direction, but this force now does not allow the particle to move along this direction. Because of this force, particle deviates from this position. When it comes here, again you can see this is the direction of magnetic field, this is the direction of velocity of the charged particle. Again force is directed towards this point. Okay, so because of this force, again particle deviate like this. When it comes here, again you can see this is the direction of magnetic field, velocity of the charged particle is this side. Now force is acting in downward direction, and that is directed towards point 2. So because of this force, again it deviates like this. When it is at this position, velocity is downward direction, magnetic field is inwards, this is the direction of force. Again you can see force is directed towards the point only. Okay, and finally it describes circular path. So whenever if charged particle enters the magnetic field now, if velocity and magnetic field are perpendicular, particle moves along a circular path, and you know that the necessary centripetal force is provided by the magnetic force. Therefore I can write QVB equals me square by r. Okay, that is necessary centripetal force is provided by the magnetic force. Using this expression we can find the radius, that is r equals me divided by bq. Okay, this is the expression for radius of the circular path when a charged particle enters the magnetic field perpendicular to it. Okay, now we know that mass into velocity is momentum. Therefore we can express this expression in terms of momentum also. Radius equals momentum divided by bq. And in the first view we studied that the relation between momentum and kinetic energy is kinetic energy equals p square by 2m. Okay, so using this I can write radius expression as r equals root 2m into kinetic energy divided by bq. This is one more expression of radius in terms of kinetic energy. Okay, or if you want you can express in terms of potential also. That is, we know that kinetic energy equals Q into V. Okay, therefore I can write R equals root 2 mv divided by b square q. Okay, so in this expression this capital V is potential. So whenever in the competitive examination, if they ask a question based on this concept, if the potential is given or potential difference is given, you can use this expression. If kinetic energy is given, you can use this expression. If momentum is given, you can use this expression. Okay, so this is expression of radius in terms of momentum, kinetic energy and potential. Okay, and if you want to find the expression for time period, you can use this expression, that is T equals 2 pi r divided by V, because time period is time taken to complete one revolution, that is distance divided by velocity, 2 pi r by V. Okay, suppose if you substitute expression for radius, that is 2 pi by V into radius is mv divided by b cube. Now you can see here velocity get cancels. So this clearly shows that time period is independent of velocity of the charged particle. Okay, time period is independent of velocity of the charged particle mainly because you can see here as the velocity increases, radius also increases. Okay, means as velocity increases in the same proportion, distance also increases. As the velocity increases in the same proportion, distance also increases, then time period remains as constant only. Okay, and in this case, when charged particle is moving along a circular path, we all know that the direction of velocity of the charged particle only changes. Magnitude always remains as constant. So this clearly shows that kinetic energy remains as constant. When kinetic energy is constant, I can say work done by the magnetic force is 0. So remember students, whenever if charged particle enters the magnetic field, magnetic field can change only direction. Okay, therefore kinetic energy remains constant because it is a scalar, it does not depend upon the direction, but momentum changes. Kinetic energy remains constant, momentum changes, and work done by the magnetic force is always equal to 0. Work done by the electric field is not 0, but work done by the magnetic field is always 0. Okay, next topic we will discuss what happens instead of a charged particle if you place a current carrying conductor in a external magnetic field. Okay, suppose if this is a direction of magnetic field, direction of magnetic field is into the plane of the board. Okay, and I will place a current carrying conductor in this external magnetic field, and I will take this as the direction of current. Now this conductor also experiences force because there is an external magnetic field, and this current carrying conductor also produces magnetic field. So again I can say there is a interaction between the two magnetic fields, that is magnetic field produced by the current and external magnetic field. Hence this conductor experiences force. That force is given by vector F equals I into L cross B. Okay, vector F equals I into L cross B. Again this expression shows that the force is perpendicular to the plane containing length of the magnetic field and external magnetic field. Okay, but in the diagram, how to show the direction of force? Remember students, force must be always shown at the position of center of mass. If the conductor is symmetric, then direction of the force must be always shown at the position of center of mass. First we will find what is the direction of magnetic force using Fleming's left hand rule. We know that if this is the direction of current, this is the direction of magnetic field, then this sum gives the direction of magnetic force. So now you fix the direction of field and direction of current. Now you can see force is acting in the upward direction. So this is the direction of force, and as I said the direction of the force must be shown at the position of center of mass. Okay, so this is the expression of force on a straight conductor. But now we will discuss how to find the expression of force on a curved conductor. Instead of straight conductor, suppose if a curved conductor is placed in a external magnetic field, okay, then if you take length of this curved conductor as L, and if you take this point as P, this point as Q, the force on this curved conductor can be found by dividing this conductor into number of small elements. Okay, because you know that this expression can be applied only for the straight conductor, but you can apply the same expression for the curved conductor when you divide this curved conductor into number of small elements. So force on each element I can write vector dF equals I into vector dl okay, vector dl cross vector b. This is force on only one element, but we are finding force on this curved conductor. Therefore, we should integrate this. When you integrate this, you will get this as F equals I into vector dl, integration is L, that is vector L. Limits I will take it as P to Q, vector dl cross vector B. Okay, then we can write vector F equals I into vector Q minus vector P cross vector B, that is vector F equals I into vector PQ cross vector B. Okay, so this clearly shows that vector PQ is nothing but this displacement. Okay, so whenever if a curved conductor is placed in an external uniform magnetic field now, and if you want to find the force on the curved conductor, then you can replace this conductor as a straight conductor. Okay, and you can say force on this straight conductor and force on this curved conductor is same. So this type of questions usually will get in higher level competitive examinations. Okay, if a curved conductor, for example, if semicircle is given, and if this semicircle conductor is placed in external uniform magnetic field now, and if you want to find the force on this semicircle, just you can replace this semicircle as a straight conductor. Okay, then I can say force on this semicircle and force on this straight conductor will be same. And remember students, the conditions, what are the conditions to replace curved conductor as a straight conductor means, the first condition is magnetic field should be uniform, and second condition is current should be same. Okay, now you can see here, from here to here magnetic field is uniform. If you take this point as P, if you take this point as Q, then you can just join the line from point P to point Q. And in the curved conductor, in semicircular conductor, you can see this is the direction of current, that is from P to Q. So in straight conductor also, you should take this as the direction of current, so that easily you can find force on a curved conductors. Okay. Then another important topic is in this chapter, that is how to find the magnetic field produced by a small element, that is using Biot-Savart's law. Okay. So first we will discuss how to find the magnetic field produced by a small element, then we will discuss how to find the magnetic field produced by the current carrying circular loop. Okay. So if you take a small element is nothing but a small portion of the conductor. A small portion of the conductor carrying current is called as current element. Okay. Current element is defined as, it is a product of current and length of the element. Okay. As you all know that current is scalar, but dl is a vector. Okay. Product of scalar and vector always gives you vector, and now we are finding magnetic field due to current element, that is a vector. Therefore we can say, according to Biot-Savart's law, magnetic field is due to vector source. Okay. But electric field is due to scalar source, that is single charge, but magnetic field is always due to vector source. And Biot-Savart's law states that if you want to find the magnetic field produced by this current element at this point at a distance r, the theta is the angle between element and the line joining point to the element. According to the statement, I can write the expression as vector dB equals mu naught by 4 pi I into vector dl cross vector r divided by r cube. Okay. Again, this expression shows that the direction of magnetic field and direction of dl. As you all know that direction of dl is always taken the direction of current. Okay. So the direction of dB and direction of dl are perpendicular, and again direction of magnetic field and direction of r also perpendicular. Okay. So dB is perpendicular to the plane containing length of the element and as well as distance between point and the element. Okay. So suppose if you take theta equals 0, if theta equals 0, then that shows that point comes on the element. Okay. Point is on the element. So in this case magnetic field is 0, that is dB equals 0. Okay. So when theta is 0, that is point comes on the element, magnetic field is 0. That is, it is 0 mainly because you know that if you take a current carrying conductor, If this is the direction of current, then this gives you direction of magnetic field lines. So magnetic field lines are only around the conductor, they are not along the conductor. That's why magnetic field paths by straight conductor at any point on its axis will be always 0. This is possible only when size of the conductor is negligible. If the size of the conductor is not negligible, then magnetic field inside the conductor is not 0. That you will come to know later. Okay. But when size of the conductor is negligible, no, I can say magnetic field path of the straight conductor at any point on its axis is always 0. Okay. So this expression gives you magnetic field paths by a small portion of the conductor carrying current, that is usually called as current element. Okay. So now we will find magnetic field paths by a circular loop at a point on its axis. Suppose if you take point P as point on the axis of the current carrying circular conductor, and if x is the distance between point and a circular conductor, and if this is the direction of current, then magnetic field paths by this circular conductor at a point on its axis is B equals mu naught by 4 pi 2 pi Ni r square divided by r square plus x square to the power of 3 by 2. This expression gives you magnetic field paths by circular loop at a point at its axis. Okay. And if you want to find the magnetic field paths by the same loop at its center, then you can substitute x equals 0. Okay. When x is 0, I can write B equals mu naught Ni divided by 2r. Okay. So this is the expression of magnetic field paths by circular coil at a point on its axis, and this is the expression of magnetic field paths by circular coil at its center. Okay. So suppose if you take ratio of these two expressions, then I can write magnetic field at the center to magnetic field at a point on its axis equals 1 plus x square by r square to the power of 3 by 2. So this expression you can directly use when you are solving competitive examination questions. Okay. That is the ratio of magnetic field paths by circular coil at its center to at a point in its axis is 1 plus x square by r square to the power of 3 by 2. Okay. So this is the expression of magnetic field paths by current carrying circular loop at a point in its axis and at the center. Okay. Now the other expression, one more expression is, you know that this current carrying circular loop behaves like a dipole. So when they are placed in external magnetic field, they experience a torque. Then the torque experienced by any dipole is given by tau equals mb sin theta. Okay. So again here torque will be maximum if theta equals 90 degrees and torque is 0 if theta equals 0 degrees. Okay. So this is the expression for torque. And one more expression is at the end we will discuss the conversion of galvanometer into ammeter and voltmeter. If you want to convert the given galvanometer into voltmeter, then you can use R equals V by Ig minus G. Okay. In this expression is R is the series resistance which is required to convert the given galvanometer into voltmeter of given range, and V is the range of the voltmeter, and Ig is current required to produce full scale deflection. If you want to find current required to produce full scale deflection, for that first you should know what is the current required for one division. Okay. That is Ig equals I by theta into N. Okay. Using this expression we can find current required to produce full scale deflection. Then V will be the range of the voltmeter. For example, if you want to convert galvanometer into voltmeter of range 0 to 3 volt, then you should take V as 3 volt, and Ig you can calculate using this expression. N will be 30 divisions, G will be given like 70 ohm, 80 ohm, 100 ohm or 120. Then you can find R value first, and this you convert in series with the galvanometer. This resistance value you connect in series with the galvanometer, so that the galvanometer act as a voltmeter. Okay. And if you want to convert galvanometer into ammeter, then the formula is S equals Ig into G divided by I minus Ig. Okay. So here S is called as the shunt resistance, which is always in parallel with the galvanometer, and Ig is again current required to produce full scale deflection. G is the resistance of the galvanometer, and I is range of the ammeter. Okay. Here V is the range of the voltmeter, but here I is the range of the ammeter. Okay. So using these expressions we can convert galvanometer into voltmeter and as well as galvanometer into ammeter. Current sensitivity, one more expression, current sensitivity is, it is current per unit deflection, that is deflection per unit current, that is theta divided by I. This is called as current sensitivity. Maybe you know the expression for voltage sensitivity also. Voltage sensitivity is, I will take it as K dash, that is deflection per unit voltage is called as voltage sensitivity. So using these expressions we can find the current sensitivity and as well as voltage sensitivity. Okay. So these formulas are important for solving the questions in moving charges and magnetism. Okay. Another important chapter is magnetism and matter. In case of magnetism and matter, basically first we will study about bar magnet. You know that bar magnet consists of two poles. One pole is called as north pole, another pole is called as south pole. The distance between north pole and south pole is called as magnetic length, or is also called as effective length. Okay. Remember students, magnetic length is different and geometric length is different. Geometric length is the actual length of the bar magnet, but magnetic length is the distance between north pole and south pole. As you all know that the poles are not exactly at the ends of the bar magnet, they are slightly inside the bar magnet. Okay. So this clearly shows that magnetic length is always less than geometric length. Okay. And magnetic length is always taken as 2L, because in case of electrostatics, the distance between two charges we used to take it as 2A, but here we used to take it as 2L, where L is distance between center of the dipole and each pole. Now we will define what is the magnetic moment of a dipole, that is a bar magnet. Magnetic moment of a dipole is defined as, it is the product of magnitude of either pole strength and magnetic length. Okay, that is 2L. Here Qm can be called as magnetic charge, and it is also called as pole strength. Okay, using this expression we can find the unit of pole strength. That is, you all know that the unit of magnetic moment is ampere meter square, and unit of 2L is meter. Therefore, unit of pole strength is ampere meter. Okay. Now we will discuss the variation of magnetic moment of a bar magnet. Okay. Variation of magnetic moment of a bar magnet. First, what we will do is, we will cut this bar magnet into number of parts along its length. Okay. When a bar magnet is cut into n equal parts along its length, its magnetic moment changes. So I want to find magnetic moment of this part. So magnetic moment of this part I will take it as m dash. Magnetic moment of this magnet is m equals qm into 2L. Okay. So when it is cut along its length, the magnetic length remains same, but pole strength decreases, because pole strength mainly depends upon area. So as area becomes, if area becomes A by n, then remember pole strength becomes qm by n. Okay. So m dash equals, I can write qm by n into 2L. Hence I can write m dash equals m divided by n. Okay. Even if you cut this bar magnet perpendicular to its length, n equal parts, again I can write m dash equals m by n only. In that case, no, pole strength remains same, but magnetic length becomes 2L by n. Therefore m dash equals m by n. And next case we will take bending of a bar magnet. Suppose if a bar magnet is bent into different shapes. For example, if it is bent into an arc of a circle, okay, and we have to find what is its new magnetic moment. So whenever if the bar magnet is bent, the effective length between north pole and south pole decreases. Therefore, magnetic moment of a bar magnet also decreases. Okay. So suppose if this bar magnet is bent into an arc of a circle, and radius of this circle I will take it as r, and angle at the center I will take it as theta. Now we will discuss how to find its new magnetic moment. Okay. If you take this distance as x, this also equal to x. So now I can say the new magnetic length is 2x. Okay. And now we will discuss how to find the x first, then we will find 2x also. That is, we can use sin theta. I have taken this angle as theta. If you bisect this, this angle becomes theta by 2, and this angle is also theta by 2. So if you use sine function, I can write sine theta by 2 equals x by r. Therefore, x equals r sine theta by 2. But we are finding 2x, hence 2x equals 2r sine theta by 2. Now we know that 2x is the effective length between n and s. Hence I can write its new magnetic moment as m dash equals qm into 2x. This equals qm into 2x. 2x is 2r sine theta by 2. Okay. But we want to express this magnetic moment in terms of its initial magnetic moment. We know that initial magnetic moment is m equals qm into 2l. Okay. So now we should express this expression in terms of 2l. For that, we know that this length is 2l. Therefore, I can write 2l equals r theta. Hence, r equals 2l by theta. So, if you substitute the expression for r in this expression, no, then you will get m dash equals 2m by theta into sine theta by 2. Okay. So, whenever if you get a question based on this concept in the competitive examination, this equation you can use directly, and you can find the magnetic moment of a bar magnet when it is bent into 1/4 of a circle, semicircle, or 3/4 of a circle. For example, if it is bent into semicircle, then you know that this theta becomes pi, because here theta is in radian. Theta becomes pi, but here theta 180 by 2, 90 degrees. Therefore, I will write here m dash equals 2m by pi into sine 180 by 2. You know that sine 180 by 2 is sine 90, which is 1. Therefore, m dash equals 2m by pi. Like this, directly using this expression, you can find the new magnetic moment. Okay. Then the other expressions are in the NCERT textbook. No derivations are not given, but expressions are given. That is magnetic field produced by bar magnet at a point on its axial line, and magnetic field produced by bar magnet at a point on its equatorial line. Okay. So I will write the first magnetic field produced by bar magnet at a point on its axial line. That is mu naught by 4 pi 2m r divided by r square minus l square to the power of r square minus l square whole square. Okay. This expression you have to use when the given magnet is not a short magnet. If it is a short magnet, then r is much greater than l. At that time, I can write magnetic field produced by bar magnet at a point in its axial line is mu naught by 4 pi 2m divided by r cube. Okay. Similarly, if you want to find on equatorial line, then magnetic field at a point in its equatorial line is mu naught by 4 pi m divided by r square plus l square to the power of 3 by 2. This expression you have to use when the given magnet is not a short magnet. If it is a short magnet, again as I said, r is much greater than l. When r is much greater than l, I can write magnetic field at a point in its equatorial line is mu naught by 4 pi m divided by r cube. So when distance is same, we can show that axial field will be 2 times of equatorial field. Okay. Okay, students. Now we'll discuss the questions on the same chapter. Okay. I will read the first question. You can see an electron and proton with equal momentum enters the magnetic field and perpendicular to it. Then the options are given. So you know that both are entering the magnetic field with same momentum. So whether they describe circular path of same radius or different radius, that we should find now. So for that we will use the expression as r equals momentum divided by bq. You know this expression. So momentum is same and charge of proton is same as charge of electron. So when charge of proton and charge of electrons are same, momentum is same, both will follow circular path of equal radius. Therefore I can say third option is correct. Okay. Now we'll move to the next question. Next question, in this question it is given that now both are having equal kinetic energies. You just compare this question with previous question. In the previous question it was question 2, it is given the kinetic energy of proton and electron is same. In the previous question it was given momentum and kinetic energy was same, but now kinetic energy is same, and you know the expression of radius in terms of kinetic energy, that is r equals root 2 m into kinetic energy divided by bq. Okay. So as in the question it is given that both are having equal kinetic energies. So when kinetic energy is same, radius mainly depends upon mass, because you know that the charge of proton and electron will be same. So radius mainly depends upon mass, and we all know that mass of electron is less than mass of proton. So in this case what happens, both will describe circular path but different radii. Okay, but in the statements you can see first statement is given as both will follow a circular path of same radius. That is not possible. Second is given as both will follow helical path. Helical path comes only when theta is greater than 0 and less than 90 degrees, means any angle other than 0, 90 and 180. Okay, and third one is given as both will follow a parabolic path. Parabolic path will never comes in the magnetism, it comes only in electrostatics. Okay, and fourth statement is given as all the statements are false. So here all the three statements are false, therefore we will take fourth option. Okay, now we will move to the next question, that is question number 3. Question number 3, in the question it is given that the charged particle is moving along a circular path, uniform circular path with a speed v, and it produces magnetic field at the center. The radius of the circle is proportional to. Then students, here many students by mistake they will use this equation, that is R equals mv divided by bq. Okay, R equals mv by bq, and if they want to find the radius, they will write as m and q are constant, they will write R is proportional to b by b. But this is the wrong answer, because in this expression now B is not the magnetic field produced by the charge, it is the external magnetic field. So now, but according to the question, we should find what is the magnetic field produced by the charge. Therefore, magnetic field produced by charge when it is moving along a circular path is B equals mu naught I divided by 2R. Okay, as you all know that this is not a current carrying circular conductor. The current is mainly because of the motion of the charge around a circular path. Okay, so current expression I can write I equals Q by T. Okay, this equals Q divided by T is 2 pi R divided by V. Now if you substitute in this expression, I can write B equals mu naught Q into V divided by 4 pi R square. Okay, then I can write R square equals mu naught QV divided by 4 pi B. You know that mu naught is constant, magnitude of the charge is constant, 4 pi is constant, therefore I can write R is proportional to root B by B. Hence we must take it as fourth option. Okay, so fourth option is correct. So remember, once again I want to repeat this in this expression, no, we cannot use this expression, because in this expression B is the external magnetic field, but we are finding magnetic field produced by charge when it is moving along a circular path. Therefore we must take this equation, and according to this solution it shows that R is proportional to root B by B. Okay, so now we will move to the next question, that is question number 4. Okay, in this question it is given that the stream of electrons are projected horizontally to the right. Okay, so electrons are projected horizontally to the right, they are moving from left to right. This is question number 4. Okay, and a straight conductor carrying current is supported parallel to the electron stream, and above it the current in the conductor is from left to right. So there is a conductor that is carrying current from left to right, and it is placed above the electron stream. What will be the effect on the electron stream? So effect is, you know that now these electrons are moving in an external magnetic field, that is magnetic field produced by this current at this place. Okay, so as the electrons are moving from left to right, the direction of conventional current is always taken in the opposite direction to the flow of electron. So this is the direction of current due to electron. So now you can see these two currents are in opposite direction. When currents are opposite direction, obviously there must be force of repulsion. Okay, so because of force of repulsion, I can say all the electrons are pulled downward direction. Therefore the electron stream will be pulled downward directions. Hence I can say second option is correct. Okay, so now we'll move to the next question, that is question number 5. Okay, so this question it is given that a particle, its mass is given, you can see the mass, and its charge is also given. It enters a uniform magnetic field, the magnitude of magnetic field is given as 1 Tesla. the speed of the particle is also given. We should find what is that distance pq. Okay, we know that charged particle is entering uniform magnetic field, and this cross indicates that the direction of the magnetic field is perpendicular to the plane of the board. Okay, and you can see here the particle enters the magnetic field such that it makes an angle of 45 degree with this line. Okay, but I can say that direction velocity of the charged particle and magnetic field are perpendicular, because you can see this is the direction of velocity of the charged particle and this is the direction of magnetic field. Okay, now you can see here velocity and magnetic field are perpendicular. Okay, so when velocity and magnetic field are perpendicular, particle describes circular path, but whether it describes complete circle or part of a circle, that depends upon how it enters the magnetic field and length of the magnetic field and radius. Okay, so first we will find what is the where is the position of center of this circular path. For that we can use Fleming's left hand rule, because if you use Fleming's left hand rule, that shows that the force is always directed towards the center of the circular path. So if this is the direction of magnetic field, this is the direction of velocity of the charged particle, now you can see force is directed towards this point. Okay, so this is the direction of force. I can take this as position of center of the circular path. So because of this force, particle deviate like this, and when it comes here, again you can see at this point, this is the direction of velocity of the charged particle, magnetic field is inverse, again force is directed towards this point. So now I can say this is center, this becomes radius, but we are finding this distance, that is PQ. Okay, so if you want to find this distance, you know that this angle is 45, this angle is 90, therefore this angle becomes 45. Okay, if this angle is 45, again as I said, the force and velocity are always perpendicular, so this angle is also 90, therefore this angle is 45. Okay, if this angle is 45, then this angle is also 45. So this, if you divide this, this angle is 90, this is 45, therefore this angle must be equal to 45. If this angle is 45, this angle is also 45. Okay, and remember students, whenever if charged particle comes out of the magnetic field, now it comes out with a same velocity and same angle, because we all know that magnetic field work, when a charged particle enters the magnetic field, now work done by magnetic field is always 0. So magnitude of the velocity always remains as constant, only direction changes, and when it comes out of the magnetic field, it comes out with a same angle, that is 45 degree only. But now we will discuss how to find this distance PQ. So if I take this distance as x, due to symmetry, this distance is also equal to x. So now I can write sin 45 equals opposite by hypotenuse, that is x divided by r. Okay, therefore x equals r sin 45. This is x, but we have to find PQ. So we know that PQ equals 2x. Okay, therefore I can write this as 2r sin 45, and you know the expression for r. R is radius of the circular path, that is 2 into r is me divided by bq. This into sin 45 is 1 by root 2. Okay, so now we can substitute the mass of the particle, that is mass of the particle is given as 2 into 1.6 into 10 to the power of minus 27, and velocity is given as 10 to the power of 7. Okay, divided by magnetic field is given as 1 Tesla. 1 into charge is given as 1.6 into 10 to the power of minus 19. So if you calculate this, you will get the answer as PQ equals 0.14 meter. You can do the calculation, I can check. I have done the substitution. So this distance PQ equals will get as 0.14 meter. Okay, so we'll move to the next question. Question number 6. As I said, whenever if charged particle enters the magnetic field with a certain angle, that certain angle with respect to this line, it always comes out of the magnetic field with a same angle. Therefore, when it enters with an angle of 45 degrees, it comes out of the magnetic field with also 45 degrees only. Hence, second option is correct. Okay. Now we'll move to the next question. Question number 7. Okay. In this question, it is given that the H plus and He plus and O plus plus ions having same kinetic energy pass through a region of uniform magnetic field, directed perpendicular to the velocity of the charged particles. The masses ratio is given, and we have to find which ions will deflect most and which ions will deflect least. Okay. Remember students, deflection can be explained either by using force or by using radius. Okay. So the best option is I will take the expression for radius. So radius expression you know in terms of kinetic energy. That is, the expression of radius in terms of kinetic energy is R equals, this is question number 7, R equals root 2 m into kinetic energy divided by BQ. You know this expression. And in the question it is given that the kinetic energy is same. Therefore, I can write R mainly depends upon root m by q. Okay. So, m is different and q is also different. Therefore, the radius will be different. So, first for the first ion, I can write R is proportional to root 1 by 1, as H plus ion mass is 1, charge is 1. Therefore, this equal to I can write 1, because when you take ratio, the proportionality constant get cancels. Therefore, directly I can write R equals 1, and for this is for H plus. Okay. Then for He plus I can write He plus is proportional to root m. M is given in the question, that is 4, and mass is 1, charge is 1. Therefore, it is 2. Okay. Then R of O plus plus is proportional to mass is given as 16 and charge is, you know that it is 2 because it is O plus plus. Therefore, it is 4 by 2, this equals 2. Okay. Now, you can see here R of He plus and R of O plus plus having same radii. Therefore, the deflection will be same for these two ions, and I can say in this question we will get two options. One is third option, which is He plus and O plus plus ions will have same deflection, and other answer is you can see H plus ions will be deflected most. Why it is deflected most? Because its mass is less, the force will be more, therefore it deflects most. Okay. For example, if you project a beam of charged particle in an inward magnetic field, okay, so all the charged particles are projected with this speed. Now, positive charged particle deflect left, that you can find by using Fleming's left hand rule. If this is the direction of magnetic field, this is the direction of velocity. Now you can see force is acting towards left. So I can say these are the path for positive charged particles. Okay. And negative charged particle deflects right. Negative charged particle you can use left hand or you can use right hand also. Suppose if you use right hand, this is the velocity of the charged particle, this is the direction of magnetic field, and this gives you direction of magnetic force. So if particles are projected upwards with a speed v, magnetic field is inwards. Now you can see force is acting towards right. So I can say this is the path for negative charged particle. Okay. So here what happens, if you use this expression, that is R equals mv divided by bq. Okay. So R mainly depends upon m and q because v and b are same. So as you know that R for H plus ions will be m for H, m and q for H plus ions will be less. Therefore, R will be less. If R is less, this is the path. If R is more, this is the path. So you can see if radius is less, deflection will be more. If radius is more, deflection will be less. So using this diagram, I can say H plus ions will deflected most, and using this expression, I can say He plus and O plus plus ions will suffer same deflection. So students, in this question, no, we'll get two options. That is option A and as well as option C. Okay. Now we'll move to the next question. That is question number 8. In question number 8, you read the question. It is given that positive ions and negative ions are subjected simultaneously to an electric field which is along positive x direction. Means electric field is along positive x direction. Okay. And in the question it is given that both ions are there along the positive x direction. That is positive ions and as well as negative ions. So you know that whenever if positive ion enters the electric field, they experiences force in the direction of electric field. So all the positive ions starts moving this direction. This is the direction of velocity of positive ions. Okay. And negative ions, according to this expression, that is F equals minus E into E. Negative ions experiences force in the opposite direction to the electric field. Therefore, all the negative ions starts moving this direction, that is along negative x-axis. Okay. This is the velocity of the negative ions. This is the velocity of the positive ions. Okay. So now you can see positive ions and negative ions are deflected in the opposite direction. But if positive ions are deflected along positive x direction, current is in the positive x direction, because you know that direction of current is always taken in the direction of flow of positive charges. But if negative ions are moving along negative x-axis, the current, conventional current due to negative ions is taken in the opposite direction. So I can write this as the direction of current due to negative ions. Okay. So now you can see current due to positive ions and as well as current due to negative ions, both are in the same direction, that is along positive x-axis. So we should find the direction of force. If finding the direction of force, you can use Fleming's left hand rule, because it can be used for current, magnetic field and force. So if this is a direction of current, this is a direction of current, and you can see magnetic field is along z direction, that is out of the plane of the board. This is a direction of magnetic field, this is a direction of current. Now you can see force is acting in downward direction. So because of this force, all the ions will deflect along negative y-axis. Therefore we must take third option. Okay. Now we'll move to the next question, that is question number 9. This is a very interesting question. This is question number 9. In this question it is given that particle of specific charge is given. You know what is specific charge? That is Q by M. That is, in chemistry we used to call it as charge by mass ratio also. So it is projected in from the origin towards the positive x-axis with a velocity of 10 meter per second in a uniform magnetic field, and the magnitude of the magnetic field is given as 2 Tesla, and its direction is given along negative z-axis. Now we should find what is its velocity after t equals 1 by 12 seconds. Okay. So one thing in the question, it is given that the velocity of the charged particle and magnetic field are perpendicular. Okay. So the particle obviously describes circular path. Suppose if you take magnetic field as into the plane of the board, okay, and if you project a particle with a velocity v, now you can see velocity is along x-axis and magnetic field is along negative z-axis. So velocity and magnetic field are perpendicular, and we are finding velocity of the particle after time t equals 1 by 12 second, because we all know that when a charged particle enters the magnetic field, when it experiences force, its direction of velocity changes. Okay, and in this case I can say velocity of the charged particle and magnetic field are perpendicular. Therefore charged particle moves along a circular path. So we should find what is its velocity after time t equals 1 by 12 second. Suppose if in 1 by 12 second particle completes one revolution, and if it comes at the same point, then I can say its velocity remains as same only. Okay, but you see all the four options are given in terms of I cap and j cap. That clearly shows that particle has not completed one revolution. But how to find that? That we can find after finding the time period. Okay, so if you calculate the time period is t equals 2 pi m divided by bq. Okay, so t equals q by m is given as pi, and magnetic field is given as 2. So it is 2 by 2 pi. Q by m is given as pi, but here it is m by q. Therefore it becomes 1 by pi. Okay. So if we cancel this, see, in the calculation of time, we should consider only magnitude of the magnetic field, because time is a scalar. It does not depend upon the direction. So we need to take minus. Okay. And if we cancel this 2, then I can write t equals 1 second. So time taken to complete one revolution is 1 second. So that clearly shows that in 1 by 12 second, the particle has not completed one revolution. Okay. Suppose if it has completed one revolution, then its velocity remains as b only. But it has not completed one revolution because it takes 1 second to complete one revolution. But we are finding its velocity after t equals 1 by 12 second. So in 1 by 12 second, we should find what is the position of the particle on the circumference. That we can find like this. See, for 360 degrees, the time taken is 1 second. Okay, 1 second 360 degrees, because it completes one revolution. When 1 by 12 second, what is the angle described at the center? So when it is projected from this point, 1 by 12 second, you will get theta equals 30 degrees. Okay, means when it is projected from this point, maybe after 1 by 12 second, this may be the position of the particle, and this angle must be equal to 30 degrees. Okay, so if this angle is 30, we are finding velocity at this point. As you know that when a particle is moving along a circular path, the direction of velocity is always along the tangential. So its velocity is changing in two directions because circular motion is two dimensions. So we should find its velocity along x-axis and as well as y-axis. Okay, so I will resolve this velocity into two components. This angle is 30, therefore this angle also becomes 30. We know that velocity and magnetic force are always perpendicular. You know that when a charged particle is moving along a circular path, the magnetic force is always directed towards the center. So this angle is 90. Okay, this angle is 30. Therefore this angle becomes 60 degrees. I'll write here. This angle is 60 degrees. We also know that this angle is 90. Therefore this angle becomes 30 degrees. Understood? Okay. Then if you resolve this velocity, you will get this as v cos 30 and this will get as v sin 30. Okay. So in vector form I can write vector v equals vx I cap plus vy j cap. Okay. So vx equals v cos 30 and vy equals v sin 30. Okay. Then I can write v equals v into cos 30 I cap plus sin 30 j cap. Okay, cos 30 I cap plus sin 30 j cap. Hence vector v equals, in the question you can see v is given as 10 meter per second. 10 into cos 30 is root 3 by 2 I cap plus sin 30 is 1 by 2 j cap. Therefore I can write v equals 5 into root 3 I cap plus j cap. Okay, so this is the answer. So in 1 by 12 second, the velocity of the particle is v equals 5 into root 3 I cap plus j cap. Hence we will take second option. Okay. Now we will move to the next question. Question number 10. In this question, it is given that charged particle enters Okay students, now we will discuss question number 10. In this question it is given that the charged particle enters the magnetic field at an angle of 45 degrees. Okay, so this clearly shows that theta is not equal to 0, theta is not equal to 90 or it is 180. So obviously it describes helical path and we have to find the radius of the helical path. Okay, so radius of the helical path we are finding in terms of pitch. So what we will do is first we will write the expression for pitch, that is pitch equals v cos theta into t. Okay, pitch equals v cos theta into t, where t is the time period. Okay, so pitch equals v cos theta into time period is 2 pi r divided by v sin theta, because you know that the circular path is mainly because of v sin theta. So if we cancel v, then I can write pitch equals 2 pi r divided by tan theta. Okay, so pitch equals 2 pi r by tan theta. Okay, so this question we are finding radius in terms of pitch. Okay, so expression of pitch is p equals v cos theta into t. Pitch equals v cos theta into time taken to complete one revolution is 2 pi r by v sin theta, because here linear motion is because of v cos theta and circular motion is because of v sin theta. Okay, so pitch equals 2 pi r by v get cancels, cos theta by sin theta you can write cot theta or you can write 1 by tan theta. So pitch equals 2 pi r by tan theta. Theta is given as 45. Okay, so theta is given as 45, tan 45 is 1. Hence we can write r equals p by 2 pi. Okay, so now we'll say third option is correct. Okay, then we'll move to the next question, that is question number 11. In this question it is given that electron moves straight inside the parallel plate capacitor. So you know that between the parallel plates capacitor there is an electric field, and in the question it is given that also filled with magnetic field. Okay, but it is moving along a straight line. Therefore what we'll do is we'll use the condition for velocity selector, that is v equals e by b. Okay, so this is condition for velocity selector. Then we have to find time taken. So once you know the distance and velocity, easily you can find the time taken, that is time taken equals distance by velocity. Here distance is L, velocity is v. Okay, so now we should find options in terms of length, magnetic field and surface charge density. Okay, we know that E equals electric field equals sigma divided by epsilon naught. Therefore, I can write time taken equals distance divided by velocity. Velocity can be written as E by B. So, E comes denominator and B goes to numerator. Therefore, it is L into B by E. So, this equals L into, since in the options they have taken magnetic field as small b in one option. So, we will take it as small b only. So, L into B divided by E, I can write epsilon naught divided by sigma. Hence, I can say second option is correct. Okay. So, now we will move to the next question, that is question number 12. So, in this question, now you can see in the diagram it is given that the given conductor is not a straight conductor. Okay, but we are finding the force on this conductor. In the synopsis, as I explained, if the given conductor is not a straight conductor and if you want to find the force on a conductor now, then we should replace this conductor as a straight conductor. Means we have to join the line between A and C. So, here this length is given as 4 centimeter and this length is given as 5 centimeter and it is a uniform magnetic field. As you all know the conditions, that is how to find the magnetic force on a straight conductor, curved conductor. If it is not a straight conductor, the conditions are, first condition is magnetic field should be uniform and second condition must be current passing through any part of the conductor should remain as same. Okay. So, here this length is 4 centimeter and this length is given as 5 centimeter. Now, this given conductor is not a straight conductor. Therefore, what we will do is we will replace this conductor as a straight conductor. For that, we have to join the line between A and C. You should join this line, that is A to C. So, if this is 4 centimeter, this is 5 centimeter, then you know that this becomes 3 centimeter. Okay. So, now we know the length of the conductor, which is 3 centimeter, and easily we can find the magnetic force. That is, a magnetic force is F equals, I will write here, BIL sin theta. Okay. But theta equals 90 degrees, because you can see if current passing through this conductor is from A to B, then it is B to C, then current passing through this conductor must be taken from A to C. So, current and magnetic field are perpendicular. So, theta equals 90 degrees. Therefore, I can write F equals BIL only. Okay. So, this equals B is given as 2 Tesla and current is given as 2 ampere into 2. Length is 3 centimeter, that is 3 into 10 to the power of minus 2 meters. Okay. We know the force, but in the question we have to find the acceleration. That is, acceleration A equals force divided by mass. This equals 2 into 2 4, 4 into 3 12, that is 12 into 10 to the power of minus 2. Okay. So, divided by mass is given as 10 gram, that we should convert into kg, that is 10 into 10 to the power of minus 3. So, if you find acceleration, you will get this along positive y-axis. Positive y-axis because force is, if this is the direction of current, magnetic field inwards, then we know that this is the direction of force. So, force is acting along y-axis and you know that direction of acceleration is always in the direction of force. So, since force is acting along y-axis, hence acceleration is also along y-axis, and its answer is 12 meter per second, because if you divide this, 10 to the power of minus 3 goes to the numerator, it becomes 10 to the power of plus 3, hence it becomes 120 divided by 10. 120 by 10 is 12 meter per second square. Hence, I can say second option is correct. Okay. So, now we will move to the next question, that is question number 13. Okay. So, in this question, you can read the question. In the question, it is given that a conducting rod of length L and mass m is moving down a smooth inclined plane of inclination theta with a constant speed. See, in the question it is given that it is moving with a constant speed. So, from the concepts of mechanics, we know that if any body is moving with a constant speed, net force acting on the body must be equal to 0, right? So, it is dynamic equilibrium. Okay. Then a current I is flowing in a conductor perpendicular to the plane of the paper and it is inwards. So, current is given as inwards. Cross indicates that current is inwards, and a vertically upward magnetic field exists in the space there. The magnitude of magnetic field is, so we have to find magnetic field in terms of mass, length and angle of inclination. Okay. So, we know that whenever if any body is placed on an inclined plane, okay, for example, if this body is placed on an inclined plane, its weight is acting in downward direction. If you take this angle as theta, if you resolve this weight, along this you will get as mg sin theta, okay, and along this you will get as mg cos theta, okay. This is mg sin theta. I will write once again, okay. So this component is mg sin theta and this component is mg cos theta, and in this case this is a normal reaction. We know that normal reaction is mg cos theta. Like that, on this conductor mg sin theta is acting in downward direction. This is the direction of mg sin theta. Now we should find what is the direction of magnetic force. So magnetic force we can find by using Fleming's left hand rule. Fleming's left hand rule says that if the first three fingers of the left hand are stretched such that they are mutually perpendicular, so that the forefinger gives the direction of magnetic field, middle finger gives the direction of current, then the thumb gives the direction of magnetic force, okay. So according to the diagram, I can write this as the direction of magnetic force, okay. If this angle is theta, then this angle also becomes theta. We know that magnetic force and current are perpendicular, therefore magnetic force is BIL. If you resolve BIL, along this you will get as BIL cos theta, okay. So this is BIL cos theta and this is mg sin theta. If this conductor has to move with a constant velocity, then these two forces should be equal. So that I will write here, that is mg sin theta must be equal to BIL cos theta, okay. But we are finding the expression for magnetic field. So magnetic field expression is, I can write B equals mg divided by I into L, okay. I into L into sin theta by cos theta is tan theta. Therefore I can write mg divided by I L into tan theta. Hence third option is correct, okay. Now we'll move to the next question, okay. Students, now we'll discuss question number 14. See, in this question it is given that electric current I enters and leaves the uniform circular wire of radius A through diametrically opposite points, okay. A charged particle Q is moving along the axis of the circular wire, passes through the center at a speed v. The magnetic force acting on the particle when it passes through the center has a magnitude, okay. So now we'll find the magnetic force on a charged particle. That magnetic force is, we know that F equals Q into V into B sin theta, okay. So we should find what is theta first. In the question it is given that current is passing through this circular conductor in diametrically opposite points. So if you take this current as I, now I can say this current equally divides, because this is semicircle, this is also semicircle. Resistance of this conductor and resistance of this conductor is same. So this current is I by 2 and this current is also I by 2, okay. So when these two currents are same, but you can see this current is clockwise and this current is anti-clockwise. So this current and this current produces equal magnitude, equal magnetic field, but the direction of magnetic field are in opposite direction. Hence I can say resultant magnetic field at the center of this circular conductor is 0. When resultant magnetic field is 0, that is if B equals 0, force on a conductor is also equal to 0, okay. Hence I can say fourth option is correct, okay. Now we'll move to the next question, that is question number 15. In the question it is given that when a certain length of wire, okay, that length I will take it as L, which is turned into a one circular loop. The magnetic induction at the center of the coil due to some current flowing is given as B naught. So when this length is turned into one loop, magnetic field at the center is given as B naught, okay. If the same wire is turned into 3 loops to make circular coil, the magnetic induction at the center of the coil for the same current will be, okay. So same length, but it is turned into 3 loops, okay. So here what happens, as it is turned into 3 loops, radius decreases, okay. So radius decreases, magnetic field expression you know, that is B equals mu naught I divided by 2R, okay. So as radius decreases, then we should find magnetic number of turns is given as N, therefore B equals mu naught, I'll write once again, B equals mu naught Ni divided by 2R. Here radius is given as A, so I will write it as 2A, mu naught Ni by 2A. First case N is 1, Now when it is turned into 3 loops, n becomes 3. So I can write b dash equals mu naught n dash I divided by 2 a dash. Okay, so you should find a dash in terms of e. So remember, length is same. Length is same in both cases. L equals L. First case it is n into 2 pi r, but n is 1. Therefore I can write first case L 2 pi r only. That is 2 pi a because radius is taken as a. Second case it is n into 2 pi a, but number of turns is given as 3. Okay, so if you find the new radius and if you solve these equations, you will get a shortcut equation as b dash equals n square into b. So since n is given as 3, therefore it is 3 square into b naught, because initial magnetic field is given as b naught. Hence we will get this as 9 b naught. Therefore second option is correct. Okay, we'll move to the next question. That is question number 16. See, in this question it is given that the magnetic field due to a current carrying circular loop of radius 3 cm at a point on the axis at a distance of 4 cm is 54 microtesla. What will be its value at the center of the loop? We know both the expressions, that is magnetic field at the center is BC equals mu naught Ni divided by 2r. Okay, and magnetic field at a point at its axis is, I will write r once again, mu naught Ni divided by 2r. At a point at its axis is B equals mu naught Ni r square divided by 2 into r square plus x square to the power of 3 by 2. Okay, in the synopsis I explained this concept, that is, if you take the ratio magnetic field at the center to magnetic field at a point on its axis, you will get the expression as 1 plus x square by r square to the power of 3 by 2. Okay, this equals 1 plus x square. Now we will see the value of x and r. X is given as 4 cm and r is given as 3 cm, and you can see magnetic field at a point on its axis is given as 54 microtesla. Okay, so 1 plus x is given as 4 cm, that is 16. R is given as value of r is given as 3 cm, that is 3 square is 9. Centimeter get cancels, whole to the power of 3 by 2. So this equals 9 plus 16, 25. 25 divided by 9. So we will get this as 5 cube divided by 3 cube. Okay, when you solve this, then magnetic field at the center equals magnetic field at a point on its axis into 125 divided by 3 cube is 27. If you substitute magnetic field at a point on its axis, which is 54 microtesla, remember it is in micro, this 54 into 125 divided by 27. 27 and 54 you can easily divide, which is 2. 2 into 125 is BC equals, it is 250 microtesla, because magnetic field at a point on its axis is in micro. Hence at the center also you will get in micro only. Okay, so magnetic field at the center is 250 microtesla. Hence we can say first option is correct. Okay, so now we will move to the question number 17. In this question it is given that a long wire carries a current of 20 ampere along the axis of the solenoid. The magnetic field due to solenoid is 4 millitesla. The resultant magnetic field at a point 3 millimeter from the solenoid axis and inside the solenoid is. Okay, so we are finding resultant magnetic field at a at a point inside the solenoid, that too at a distance of 3 millimeter from the axis of the solenoid. Okay, so if you take a current carrying solenoid, you know that magnetic field produced by current carrying solenoid is always along its axis. Okay, suppose if you take this as the direction of current through the number of turns in the solenoid, I can write this as the direction of magnetic field produced by the solenoid. So I will take it as BS. BS is nothing but magnetic field produced by the solenoid. Okay, now we are finding magnetic field produced by another wire which is kept along the axis of the solenoid. So that I will write length of the wire is L and it is kept along the axis of the solenoid. Okay, and current passing through this wire I will take it as I. Okay, this is the direction of current. So now we should find magnetic field produced by this current at a point 3 millimeter from the axis of the solenoid. You can take at a point above the wire, or you can take at a point below the wire, you will get the same answer. Suppose if you take at a point below the wire, if you want to find at this point, so according to this right hand thumb rule, you know that direction of magnetic field produced by this current at this point is inwards. This is the direction of magnetic field. So magnetic field produced by this current is inwards, but magnetic field produced solenoid is this direction. Okay, this cross indicates that magnetic field produced by this current carrying wire at this point is inwards. So this magnetic field and this magnetic field are perpendicular. Therefore I can write B equals root of magnetic field produced by the conductor square plus magnetic field produced by solenoid. Okay, I think in the question magnetic field produced solenoid is given. That is, magnetic field produced solenoid is given as 4 millitesla. Just we have to find what is the magnetic field produced by long wire. We know the expression of magnetic field produced by long wire. That is, magnetic field produced by conductor is mu naught I divided by 2 pi r. This equals 4 pi into 10 to the power of minus 7, and current in the wire is given as 20 ampere. Okay, current is 20 ampere divided by distance is given as 3 millimeter. Okay, so 3 into 10 to the power of minus 3, and magnetic field plus solenoid is given. So if you substitute and if you calculate, you will get the answer as 4.2 millitesla. Okay, so I will write the answer directly. You can do the calculation. It is 4.2 millitesla. Hence I can say second option is correct. Okay, so now we'll move to the next question. That is question number 18. See, in this question it is given that a straight wire of length pi square meter. Here pi square approximately you can take 10 meter. Okay, carrying current of 2 ampere and a magnetic field due to measured at a distance of 1 centimeter from it. If the wire is bent into a circle and is to carry the same current as before, the ratio of magnetic field at its center to that obtained in the first case should be what? Okay, so first what we'll do is we'll find the magnetic field produced by straight conductor. Okay, so magnetic field produced by straight conductor is take approximately 10 meter. So length is 10 meter, but distance is given as only 1 centimeter. You can see distance is only 1 centimeter. So this conductor can be considered as very long straight conductor. For very long straight conductor, the expression of magnetic field is B equals mu naught I divided by 2 pi r. So I will take this magnetic field as B1. Okay, so B1 equals mu naught I divided by 2 pi, r is given as 1 centimeter, that is 10 to the power of minus 2. I will take this as equation 1. Okay, now we will find magnetic field produced by circular conductor. Same length is bent into a circle. Okay, and same current is passed. Radius I will take it as r. We know the expression of magnetic field produced by circular conductor at its center, that is B2 equals mu naught I divided by 2r. Okay, so we have to take the ratio of these two magnetic fields. For that we should cancel this r. So r we can express in terms of L, that is we know that L equals 2 pi r. Therefore r equals L divided by 2 pi. Okay, so now I can write B2 as B2 equals mu naught I divided by 2 into r is L divided by 2 pi. Okay, so 2 you can cancel. Then I can write B2 equals mu naught I divided by pi divided by L. Okay, so now what we'll do is we'll take the ratio. If you take the ratio of B1 by B2, see B1 by B2 ratio if you take, then I can write B1 divided by B2 equals, if you substitute all the values, you will get this as 1:50. So I will write the answer directly. Later you can do the calculation. Okay, so second option is correct. Now we'll move to the question number 19. See, in this question we should find what is the magnetic field produced by square which is having n turns at its center. Each side is given as 2L. Okay, square each side is given as 2L. Then distance between square has 4 straight conductors. So you can take direction of the current as clockwise or you can take anti-clockwise. You will get the same answer. So first what we will do is we will find the magnetic field produced by only one conductor at its center. So if this length is 2L, then this length becomes L. So if you join the line from one end of the conductor to point, this point, and other end of the conductor to this point, these two angles becomes 45 degrees. This angle is 45 and this angle is also will get as 45. Okay. So magnetic field parts by only one conductor is B equals mu naught I dot by 4 pi r. You know this expression, into sin theta 1 plus sin theta 2. This is magnetic field parts by only one conductor. But you can see all current is clockwise. Therefore, at the center of the square, all the conductors produces magnetic field in the same direction. Hence, I can write total magnetic field as B dash equals 4B. This equals 4 into mu naught I dot by 4 pi r into sin theta 1 plus sin theta 2. That is sin theta 1 is 45 and theta 2 is also 45. That is sin 45 plus sin 45. Okay. So 4 you can cancel, and in the question it is given that the loop has n turns. Therefore, I will write it as into n. Hence, it is mu naught ni divided by pi into r is given as, see, each side length is given as 2L. Therefore, r becomes L, pi into L into 1 by root 2 plus 1 by root 2 is 2 by root 2, 2 by root 2 is root 2. Therefore, finally, I can write root 2 mu naught ni divided by pi into L. So, this is the answer. Hence, we will take this as first option, that is root 2 mu naught ni divided by pi into L. Okay. So, now we will move to the next question, that is question number 20. When the current flowing in a circular coil is doubled and the number of turns of the coil is half, the magnetic field at its center will become. Okay. So, current is doubled, number of turns becomes half. We should find the magnetic field at the center. So, radius of this coil I will take it as r. Magnetic field at the center, we know that B equals mu naught ni divided by 2r. Okay. So, in the question it is given that current is doubled but number of turns becomes half. We know that as number of turns changes, radius also changes. Remember friends, if number of turns becomes double, radius becomes half. That you can prove by using this expression. In both cases, length remains same. Okay, L equals L. But first case, L is n into 2 pi r. Second case, L equals, as in the question it is given that number of turns becomes half. Therefore, it is n by 2 into 2 pi r dash. Okay, so r dash becomes, r dash equals, if you cancel this n, r dash becomes 2r. Therefore, I will write in the next slide, B dash equals mu naught, n is given as n by 2, current is doubled, that is 2I, okay, divided by 2 into radius becomes now 2r according to this expression. Okay. So, if you cancel n and r, I can write this becomes B dash equals B by 2. Okay. So, it becomes half. By mistake, what we will do is, we will not consider radius, we will take directly n by 2 and 2I, and we will cancel this 2 and 2 and we will say it remains as same. But you can see here from this expression, we can see when length is same, if you number of turns becomes half, radius becomes double. Suppose if you increase the number of turns as 2, then radius becomes half. So, always you should remember this expression. This is very important. Okay. So, B dash equals mu naught n by 2 into 2I divided by 2 into 2r. Hence, I can write B dash equals B by 2. Okay. So, hence we will take this as third option. Now, we will move to the question number 21. Okay. 21, a long straight wire of radius A carries a steady current I. The current is uniformly distributed across its cross section. So, after reading the question only, we can say the size of the conductor is more. As I said in the synopsis, that is, if size of the conductor is negligible, then magnetic field produced by the conductor at any point on its axis is 0. But if size of the conductor is not negligible, then magnetic field produced by conductor at any point in its axis is not 0. Okay. So, you will use this concept. We means we are using the concept of Ampere Circular Law and we will solve this question. the ratio of magnetic field at A by 2 and 2A is. Okay. So first we should find magnetic field at A by 2, then we should find magnetic field at 2A. Okay. So size of the conductor, as I said, size of the conductor is not negligible, size of the conductor is more, and we have to find magnetic field produced by this conductor at a point inside and at a point outside. Okay. And radius of wire is given as E. See, radius of this circular cross section is given as E. I will take this as a center, then this becomes radius, that is A by 2. Okay. So we know the expression of magnetic field produced by this current carrying conductor according to Ampere Circular Law. I can write that as B1 equals mu naught I dot by 2 pi A square into R, where R is radius of the Amperian loop. Okay. R is radius of the Amperian loop. I'm sorry, radius of this loop is given as A, and radius of Amperian loop is taken as A by 2. Okay. So radius of Amperian loop is A by 2 means we are finding magnetic field at this point. This loop is called as Amperian loop. So this radius is A by 2. So R will substitute it as A by 2. Okay. Then I can write B1 equals mu naught I dot by 2 pi A square into R is A by 2. Okay. This loop is called as radius of the Amperian loop. Now we are finding magnetic field at this point, that is at a point P inside the conductor. Okay. So that is B1 equals mu naught I dot by, if you cancel 1A, then I can write 4 pi A. I will take this as equation 1. This is magnetic field produced by the conductor at a point inside the conductor. At a point outside the conductor, you know the expression, directly you can use that. That is B2 equals mu naught I dot by 2 pi R. But in the question, first I will write R, then we will substitute for the R. Remember, R is the radius of the Amperian loop, that is at a point outside the conductor. In the question it is given that outside the conductor the radius is 2A. Okay. So R will substitute it as 2A. That is B2 equals mu naught I dot by 2 pi into radius is 2A. So B2 equals, will get as mu naught I dot by 4 pi A. This is equation 2. Now we know the two magnetic fields. One is at a point inside the conductor and other one is at a point outside the conductor. Outside the conductor at a radius of 2A. Okay. So if you take the ratio, then I can write B1 divided by B2 equals 1. Okay. So third option is correct. Okay. So now we'll move to the next question, that is question number 22. What will be the resultant magnetic field at the origin due to 4 infinite length wires? We know the expression of magnetic field produced by infinite length wires, that is B equals mu naught I dot by 2 pi R. Okay. We know the expression. Anyway, we are not using this expression here because all the options we have to express only in terms of B, not in terms of mu naught, current or distance. Okay. So if each wire produces magnetic field B at the origin, then what is the resultant magnetic field? So here I can say it only depends upon the direction, because you can see distance is same, current is same. Okay. But the direction of currents are different. These two currents are given as outwards and these two currents are given as inwards. So we have to find the resultant magnetic field at this point. Okay, at the origin. So whether it can be 0 or it can be 4 times or it can be root 2 times or it can be 2 root 2 times. So that we will find out. That, as I said, no, it mainly depends upon direction of magnetic field. So direction of magnetic field produced by this current at this point is upwards. I will write here. Okay, magnetic field produced by this current at this point is, magnetic field produced by this current is upward direction. This one magnetic field. Similarly, magnetic field produced by this current at this point is towards right. That is magnetic field produced by this cross. That is this direction. You know how to find the direction of magnetic field by using right hand thumb rule. Then direction of magnetic field produced by this current, that is inwards, is again this direction. For that also you can use right hand thumb rule. Then direction of magnetic field produced by this current at the same point at the origin is this direction. So these two magnetic fields are upward direction, these two magnetic fields are towards right. Okay. So this resultant becomes 2B, this resultant is also 2B. Okay. So this angle is 90 degrees. So final answer I can write BR equals root 2B square plus 2B square. Okay. If you find the resultant, you will get this as third option. Hence, answer resultant magnetic field at the origin, we can say it is 2 root 2B. Okay. So now we'll move to the next question. That is question number 23. Here, 3 conductors are given. One conductor is complete circle. We should neglect this gap. And other one is 3/4 and one more is also 3/4. For this complete circular conductor, the radius is given as C, and for this conductor, the radius is B, and for one more conductor, the radius is A. Okay. So now we should find resultant magnetic field at the center. So resultant magnetic field we should find due to the circular conductor and to 3/4 of the conductor. For circular conductor, I will write here only. That is, I will take it as B1. B1 equals mu naught I divided by 2R, but R is 2C. Okay. So I will take this as equation 1. Now direction of this magnetic field is, you can see current is clockwise. If current is clockwise, magnetic field is inverse. So this magnetic field is inverse. Okay. Then we will find magnetic field passed by this 3/4 of the conductor. What is the current passing through this 3/4 of the conductor? That is anti-clockwise. Therefore, I can write that magnetic field as B2 equals, you know that 3/4 magnetic field is, you should multiply this with 3/4. That is 3 mu naught I divided by 8, radius is given as B, 8B. Okay. So this current is anti-clockwise, therefore magnetic field is outwards, that is dot. I will take this as equation 2. Okay. Then one more 3/4 of the conductor is given, but current passing through this conductor is given as clockwise. Okay. And its radius is given as A. So that magnetic field I will take it as B3. That is B3 equals 3/4 magnetic field is 3 mu naught I divided by 8A, and it is inverse because the current is clockwise. This is equation 3. Okay. Now we know the magnitude and direction of magnetic field passed by one complete circular conductor and 2 3/4 of the conductors. Okay. We should find what will be the magnetic field at point P when resultant magnetic field is given as 0. Then what should be the relation between A and B? That we should find. Okay. If resultant magnetic field has to be 0, then you can see these magnetic field must be equal and opposite. But here the two magnetic fields are in one direction, another magnetic field is in the opposite direction. Therefore, resultant has to be 0 means I must write the condition as B1 plus B3, because they are in the inward direction, must be equal to B2. Okay. That is mu naught I divided by 2C plus 3 mu naught I by 8A. 3 mu naught I divided by 8A. Okay. Must be equal to 3 mu naught I divided by 8B. Okay. Because resultant has to be 0. And in the question it is given that C equals 2A. So C equals 2A if you substitute, then I can write mu naught I divided by 2 into 2 is 4A plus 3 mu naught I divided by 8A. This equals 3 mu naught I divided by 8B. Now you should simplify this and you should find the relation between A and B. If you simplify and if you find the relation between A and B, you will get this as A equals 5 by 3 B you will get. Therefore, we will take this as third option. Okay. Now we will move to the next question, that is question number 24. A current carrying closed loop in the form of a right angle isosceles triangle ABC is placed in a uniform magnetic field acting along AB. If the magnetic force on the arm BC is F, magnetic force on the arm BC is given as F. Okay. So on this magnetic force is given as F. The force on the arm AC is force. Now we should find what is the force on arm C. Okay. See, the basic concept is whenever if you place a closed loop in a uniform magnetic field, remember it can be a triangular loop or it can be a circular loop or it can be a square. Any closed loop if you place in a uniform magnetic field now, then net force acting on the loop must be always equal to 0. Okay. So net force acting on this loop must be equal to 0. Whatever may be the direction of current. Direction of current may be clockwise or anti-clockwise. Remember, if the magnetic field is uniform now, uniform magnetic field, if you place a closed loop, any closed loop, the resultant magnetic force must be always equal to 0. Okay. So now I can write net force acting on this loop must be equal to 0. If net force has to be 0, then force acting on, it's a vector sum, force acting on AB plus force acting on AC plus force acting on BC, okay, must be equal to 0. Now you can see here, suppose if you take current as clockwise, okay, current as anti-clockwise, then magnetic field and current are same direction. So force on this conductor, angle between, for this conductor, angle between current and magnetic field becomes 0. Hence I can say force on this conductor is 0. Okay. So when even if you take current as anti-clockwise or clockwise, in one case if theta is 0, other case theta becomes 180. But anyway, force on conductor AB is always equal to 0. So 0 plus force on conductor AC plus force on conductor BC equal to 0. So now I can write force on conductor AC must be equal to minus force on conductor BC. So suppose if you take this force as F now, this force must be equal to minus F. Hence we must take second option, that is B. Okay. Okay. So now we'll discuss question number 25. See, in this question the paramagnetic substance is given, that is important first, because based on this substance only we can use the relation. And one temperature is given as minus 73 degrees Celsius and other temperature is given as minus 173 degrees Celsius. Okay. Susceptibility at one temperature is given and we should find susceptibility at other temperature. So if you use Curie's law, we know that susceptibility is inversely proportional to absolute temperature. As I said, absolute temperature, you all know that it must be taken in Kelvin. Okay. So we are finding susceptibility in the second case. Therefore, if you divide this susceptibility in the second case at temperature T2 and susceptibility at temperature T1 equals, I can write T1 divided by T2. Okay. So this equals T1 is minus 73, as degree Celsius is given, we should convert into Kelvin. So this becomes 200 if you convert into Kelvin, and this becomes 100. Okay. So this equals 2. Hence I can write susceptibility in the second case equals 2 into susceptibility in the first case. So it is given as 0.0060. If you multiply with 2, you will get it as second option. Okay. So this is question number 25. Now we'll move to the question number 26. In the question number 26, if you read the question, a bar magnet is hung or suspended by a thin cotton thread in uniform horizontal magnetic field and it is in equilibrium. In the question it is given that the magnetic field, bar magnet inside the magnetic field is in equilibrium. It is a stable equilibrium. The energy required to rotate it by 60 degrees given as W. Now the torque required to keep the magnet in this position. In this new position means initially it is parallel to the direction of magnetic field, but now new position is it is at an angle of 60 degree. Okay. So we are finding torque at this position. Therefore, we should use the expression as tau equals mb sin 60 degrees. This equals mb into sin 60 is root 3 by 2. Okay. But you can see all the options are expressed in terms of energy, that is W, work done. So what we'll do is we'll take this as equation 1 and we'll find the work done. We know the work done equals, see students, when magnetic field is in equilibrium, initially you should take theta as 0. So directly we can write work done equals 1 minus mb cos theta, 1 minus cos theta into mb. Okay, because the complete expression is work done equals cos theta 1 minus cos theta 2, but in the question it is given that it is in equilibrium. Therefore, initial value of theta should be taken as 0. As you know that cos 0 is 1, hence it is work done equals 1 minus cos theta into mb. And new position of theta is given as 60 degrees. That will substitute here. That is 1 minus cos 60 is 1 by 2. So 1 minus 1 by 2 into mb. So 1 minus half is half. Therefore, I can write mb equals 2 times of work done. That will substitute in this equation. Okay. So if you substitute in this equation, I can write torque equals mb is 2w into sin 60 is root 3 by 2. Okay. So it is into root 3 by 2. So 2 you can cancel. Then I can write torque tau equals root 3 into w. Okay. So hence we must take it as third option. Third option is correct. Okay, so now we'll move to the next question, that is question number 27. See, in this question it is given that a bar magnet of length L and magnetic dipole moment M is bent in the form of a arc. Okay, so the new magnetic dipole moment is magnetic dipole moment of this magnet we should find. As in the synopsis, I given on shortcut equation to find the new magnetic moment, that is M dash equals 2m by theta into sine theta by 2. Okay, I already explained this equation. Here theta is in radian, so 60 degree it is becomes pi by 3. Therefore, I can write 2m divided by pi by 3. Okay, into sine theta is, as theta is 60, theta by 2 is 30, sine 30 is 1 by 2. So this 2 you can cancel. 3 goes to the numerator. Therefore, I can write it is 3m divided by pi. This is the answer. Therefore, we should take it as fourth option. Okay, hence fourth option is correct. Thank you, students. All the best.